Hello everyone, welcome back to Aerospace Lab 2, another lecture. This week we are going to talk about vibration a little bit. We will see a little bit of background in vibration theory. In this background we will talk about theory behind the free beam vibration. We'll see the nodal analysis and the equations, all of the theory behind it, and then we will move on to the cantilever beams. Again, a theoretical analysis, and then we will talk about the experiments. You just have to keep in mind that we are planning to have a 2-week experiment. For this vibration analysis. In the first week, you will learn how to use the LabVIEW software to essentially write a code to extract the data, which is going to happen in September 24th. For the lab afterwards, we will essentially do an experiment on vibration of the beam. Which is going to happen on October 1st. So your lab 4 and 5 are essentially both of them are gonna be focused on vibration. The first one is going to be for you guys to focus on LabVIEW software, which is a very useful software to learn for experimental analysis, and it is very widely used in the industry if you are involved with research and development, R&D, of course. Okay. So moving on, what is the objective of this lab? Eventually, in the objective, keep in mind that for these two labs, you only have to write one lab report. Okay. The objective of this lab, the first objective is learn how to calculate the theoretical natural frequencies and nodal positions of a beam modeled as free or cantilever beam, which we will discuss today. And you have to do the calculations for the beam we have in the lab, and then you're gonna verify your calculations with experimental results. You have to draw a conclusion to how the beam can be best modeled, free versus cantilever, and you will learn how to calculate the damping ratio of the beam vibration. But what is vibration in general? Vibration is a mechanical phenomenon in which oscillations will occur. So it will look vibration. It will look something like this. Right? It is a mechanical phenomenon, of course, and you have oscillations, as you can see here. Okay. Free vibration occurs when a mechanical system is set in motion with an initial input and allowed to vibrate freely. So we're talking about the free vibration. We need to have an initial input, and your system must be allowed to vibrate freely. That's when the free vibration happens. Okay. But forced vibration is when a time-varying disturbance, like a load or displacement of the velocity, is applied to a mechanical system. So most of the examples we're going to see are going to be focused on the forced vibration. A periodic and a steady-state input. The input can be periodic, steady-state, transient, or random. But what is the difference between the force-free and the damped vibrations? Damped vibration is when the energy of the vibration system is gradually dissipated by friction and other resistances, and these vibrations are damped. So when you have just an initial disturbance that is going to cause forced vibration in your system, you don't have a periodic disturbance happening influencing your system, your vibration will always be damped eventually. Yeah. Vibrations are can be always modeled with a spring mass damper system. So you have a mass, you have a spring, and you have a damper C, right? And the displacement happens in this direction and this direction, of course, right? If you want to find the force balance in the system, or if you want to draw the FBD, the free body diagram of the system, it will look like something like this. You have the mass, you have an elastic force that is there because of the presence of a spring, you have a damping force that is there because of the presence of the damper, you have your force that is usually a function of time, and you always have your inertial force that is going to act in the opposite direction to your force. Okay, so the general equation for vibration is going to look like this. It's going to be mx double dot plus cx dot plus kx equals to 0, right? You have to keep in mind that x double dot is always a derivative of x with respect to time. The second derivative x dot is the derivative of x with respect to time. Okay, and if you assume that you don't have a damped vibration, then this term will vanish and you will get this as your main equation. But what will be your mode shape like? Your mode shape is going to look like this. Your x is going to be equals, this is a general mode shape, a sine of k over m t plus b cosine of square root of k over m t, right? And this square root of k over m is called the natural frequency of the system. Yeah. So your mode shape is going to look like something like this. Okay. Okay, something like this. Okay, actually, this mode shape can change a bit by something that is called the phase shift. The phase shift can move the mode in the t direction, right? And that will be present in your general equation as a plus phi in the sine and cosine functions. Okay. We will talk about this in a little more detail later. But what is the resonance? Resonance happens when the frequency of external exciting force is equal to the natural frequency. Then the amplitude of vibration becomes excessively large. Okay. Resonance is of course very dangerous and may lead to failure of major structures. To give you two famous examples, two of the famous examples of this, we can talk about the Broughton suspension bridge. I'm pretty sure you are familiar with the most famous resonance case that happened in the United States in the 1940s. But we are going to talk about a little less famous cases, right? The Broughton suspension bridge was developed by architects in the 19th century England, United Kingdom, in the city close to the city of Manchester, which is in the city of Broughton, essentially. And what happened was when they opened the bridge and one day soldiers were marching on this bridge, and the natural frequency of the bridge became very close to the natural frequency of the soldiers marching on the bridge. So a very dangerous resonance happened and essentially caused the failure of the bridge. And after this, the armies all around the world, whenever soldiers are moving on a bridge, the armies order them to break the steps on the bridge, which means essentially they have to go out of a step when marching on a bridge. And the other case is the Millennium Bridge in London again, which was uh, open, which was supposed to open in the early 2000s, and it opened in I think 2001, and it was a pedestrian crossing essentially. The natural frequency of the bridge became was very close to the walking. There's a step frequency of the pedestrians that were walking on the bridge. So what happened was people were seeing a lot of big movement on the bridge, and they couldn't control this, and they couldn't walk on the bridge essentially. So they had to close the bridge and work on it for 2 years to reopen it. The problem with this one was that the natural frequency of the soldiers marching on a bridge, or the train moving on a bridge, or the cars moving on a bridge were well known up until this point, but the natural frequency of random people walking on a bridge was not known. Right? So the architects and the engineers, civil engineers, didn't take that into account when designing the bridge. So as you can see, the resonance can be very dangerous and sometimes fatal, and we always have to keep that in mind. One other very famous resonance that happened, let's define resonance again, and then we'll talk about this next case. Resonance is a phenomenon that occurs when the frequency at which a force is periodically applied is equal or nearly equal to one of the natural frequencies of the system on which it acts. This causes the system to oscillate with larger amplitude than when the force is applied at other frequencies. So one very famous case that happened in 2009. That happened in 2009 happened in the International Space Station. So, and it is mostly controlled by computers, and it is on autopilot. But the command that the autopilot received was essentially to increase the vibration of the system, and this is what happens there. As you can see, the International Space Station is vibrating, and I assume for the astronauts there, it should have been a very scary moment, right? You are in the space, and your home essentially it starts vibrating. Okay, so again, to put it in more theoretical terms, we can see the natural frequency versus the input frequency here. And this delta, actually, this delta here, that is representing your representing the distance from the distance of the input frequency from the natural frequency. As you can see, for larger deltas, we don't get any oscillations. Everything is going to be normal. But then as you decrease the delta, and the delta becomes zero, it means that your natural frequency or input frequency are coming closer, and this is where the disaster happens, when delta becomes zero. Okay, and this is where you're going to see very high oscillations that you don't want to see normally. Okay, But as mentioned before, what we are going to talk about, and this is the beam you're going to see in the lab, is the beam vibration. We are going to design an experiment to study the vibration characteristics of a beam. We want to calculate the natural frequencies and mode shapes. We want to measure the natural frequencies and mode shapes. And we want to determine which model, free or cantilever, can best describe the beam. As you can see, this can be modeled as 2 cantilever beams or 1 free beam. Right? We want to see which theoretical model fits this best. So let's watch this video. It's a 4-minute video, 4-minute long video that's talk about focuses on the theory of the free beam. It's a very interesting. I think it goes into very good details. Talk about a very good details. Talk about different modes of the free beam, and then we'll get into the mathematics behind it. So distortional modes actually become, I'm not sure if you have gone over distortional modes in your vibration course, but these torsional modes are very important in aerospace industry or industry in general, if you want the vibration industry, vibration focus industry, because when you're dealing with the plates, you have to make sure that you understand these torsional modes, right? So whatever you have learned so far in your vibration code has been focusing on the rod vibration, if you will. But the torsional modes and the plate vibration are also very important, which is of course out of the scope of this course, but I just wanted to include it in this video so you guys are well aware that this is something that is out there. Okay. Okay, I guess that's it. So hopefully this video has given you a very good idea of what free beam vibration is. And let's talk about the theory of it. So essentially, as you can see here, this is a schematic of a free beam, right? We have displacement in this direction, so perpendicular to the length of the beam. Area of the beam is B multiplied by H. The moment of inertia that you are interested in is going to be BH cubed over 12. For a still, if you're dealing with a still, 200 gigapascals, and these are the values you have to use in the lab. And the density of this is still is going to be 7,800 kilograms per meters cubed. But if you we have two types of beams in the lab. So if you were to deal with aluminum, then E is going to be 69 gigapascals, and density is going to be 2,700 kilograms per meters cubed. Okay, and we have all the lengths and all the other parameters as well. So this is the beam we are going to deal with, but you will see all of the information in the lab instruction and also in the lab as well, if not in the lab instruction. Okay. But what is the universal vibration equation? We have seen the equation, another equation that is only dependent on time, but displacement is going to change with location as well, right? So we have to come up with a formula that is a function of time and location. Right? This is going to be your general formula, your density multiplied by the cross-sectional area, the second derivative of displacement with respect to time, plus gamma, which we'll talk about a little later, the first derivative of your displacement with respect to time, and the modulus of elasticity multiplied by moment of inertia, plus the fourth derivative of displacement with respect to location. All of this is going to be equal to 0. So your cross-sectional area, as we have mentioned, can be calculated by B multiplied by H. Your gamma is the damping term for internal energy loss. Rho is the density. Young's modulus is E, and I is your moment of inertia, BH cubed over 12. And as I mentioned, your W dot is the first derivative of displacement with respect to time, W double dot, a second derivative of displacement with respect to time, and the primes are the derivatives of displacement with respect to location, or the distance, displacement in the other direction, essentially. All right. Okay, and you have to keep in mind that W is the displacement normal to the length of beam. So whenever we are talking about, just to make everything clear, let's say this is your beam, W is displacement in this location, and this is X. Okay, so let's rewrite the equation and let's try to see what kind of solution we can have for this. What you want to do is to make the equation a little simpler. So we divide the equation by density multiplied by the cross-sectional area, and then we come up with some parameters. M, your mass, is going to be equal to density multiplied by the cross-sectional area multiplied by the length of the beam, and we also have the damping factor. C is square root of EI divided by rho multiplied by your A. So if you plug those in, if you simplify the equation, you are going to get to this final equation. W double dot plus gamma L over M is W dot plus C square over gamma 4 prime. A fourth prime is going to be equals to 0. Okay. But how can we solve this equation? We are not going to go into the solution that much, how to get to the final solutions, because it is already very in-depth, what you're going to see later. But whenever you're dealing with this type of problems, when you have a derivation with respect to time and with respect to location, or meaning that you have two independent variables, you want to use one of the methods you want to use is the separation of variables, right? So what is separation of variables? Is that the separation of variables is to transform the function, which is a function of two variables, to the multiplication of two functions, which one of them is a function of just location, the other one is a function of time for this specific case. So your W, which is displacement of x and t, is going to be equal to one function that is only a function of x multiplied by one function that is only a function of time. And then we are going to find a solution for each of them separately. So one solution, two solution. Your final solution is essentially going to be a multiplication of the two solutions. That's it. Okay. So to advance this further, you can essentially I don't want to go into details here, but this is what you are going to get as the two separate functions, right? So the function, let's call it, here we have called it g of t, but here we have called it t of t, but these are the same functions, is going to be equals to t double prime plus gamma L over m t prime over t, and that is equals to, because these two have to be equal, right? A minus c squared x fourth prime over x, and all of them is going to be equal to negative omega 2. These are all constants. Okay. Yeah, so just accept this from me. This is going to be the formulation you will be getting from here. I'm not going to go into detail about this, but if you end up taking a higher level vibration course or higher level heat transfer course, you will definitely see how to get from this to this, how to get from this to this. Okay, so moving on. So we solve each function f of x, this one and this one separately. 1 and 2, 1 and 2 separately. Okay, so first step is to solve the equation, the spatial function or the location based function. Recall that the function was like this, so negative c squared x fourth prime over x is equal to negative omega 2 omega squared. You can rewrite this function as this by defining this new parameter beta. So beta 4 is going to be equal to omega squared over c squared. Okay. And when beta is not equals to 0, we know the general solution is gonna look like this. X of x is going to be equal to coefficient 1, a1, sine of beta x plus a2 cosine of beta x plus a3 hyperbolic sine of beta x, and a4 hyperbolic cosine of beta x. But to solve this problem, to find these coefficients, we need to have the boundary condition. So the boundary condition for the case of the free beam, for which this is the governing equation, are two. We have zero moments at both ends, which means that at each time your EI omega double prime is going to be equal to EI omega double prime of the other end is going to be equal to 0, which means that the x function, because we have to transform that function, right? to the new function. Your x function at x and L is going to be equal to 0. So these are two boundary conditions, but we have four coefficients, so we need four boundary conditions. The other boundary condition is the zero shear stress at both ends. So if you do the same analysis, you get to this final boundary condition. So the second derivative of your location at x and L is going to be equal to 0. That's your first and second boundary condition. And the third derivative of your displacement with respect to location at both ends of the column is going to be 0 as well. So you plug those equations in, you plug those boundary conditions in, you have the main equation from the previous slides. To be able to plug these in, you have to take the first and second derivative of this main function, the second and third derivative of this main function, then plug the boundary conditions in. Pretty sure you are familiar with the procedure at this point. And this is going to be the final thing you're going to get. So your A4 is equals to A2 and A3 is equals to A1. So based on this, we can rewrite the equations as following. We can just replace A1 and A3 and A4 by A1 and A2 and just pack them together, get the equations together, like take A1 and A2 out essentially. And this is equals to a system of equations, a matrix of B, which represents this, multiplied by the matrix of A, which represents the coefficients, is going to be equals to 0, where matrix B is this. Okay? So since we have the systems of equations, it's going to be easier for us to solve using the numerical methods and all of the methods we have previously learned. But a generalized solution for this type of problems is going to look like this. So you'll end up with this solution, cosine of beta n L multiplied by the hyperbolic cosine of beta n L is always equals to 1, where beta n to the fourth is going to be equal to omega n to the fourth over c squared, in which c is the square root of ei over rho a. Okay. So beta is a periodic function. As you can say, it depends on your modes, right? For mode 0, we are going to have beta 0L for a rigid body, which means that we are dealing with a rigid body, which means that your beta NL is gonna 0, and we have the different values for each modes of beta and L. Okay, and for beta n's larger than 5, you can essentially come up with this equation to calculate beta L. Okay. But based on this information, the final goal is to find the natural frequency. That's what we're going to find. Right? How can we find the natural frequency? So using beta and C, we can always find Wn. And if you divide Wn, omega n, by 2 pi, you're going to get your natural frequency in the units of hertz per second, right? Instead of radians per second, we're going to have hertz. Right? You just plug omega n in, and this is going to be your final equation for natural frequency, and in which n refers to the modes that you are in. And we'll talk about modes. You saw that in the video. You saw what the different modes are, but yeah, we will talk about them a little later. L is the length of the beam. E is the Young's modulus. I is the moment of inertia. Rho is the density, and A is the cross section. If F is going to be the frequency, which means the cycles per second or hertz, and omega is the frequency in radians per second. But how can we find the value of the displacement? We essentially have to go back and try to solve the equation to find the value for the coefficients. And then I'm not going to go into details for this, but this is going to give you your final displacement in which you have the A2 as the coefficient and you have a new variable sigma n. Okay, a sigma n is essentially, sorry guys, yeah, sigma n is essentially this value. So using this very huge function, you can find the mode of the displacement, the shape of the displacement, deflections. Yeah. And this is going to be very helpful in finding the nodal position or the nodes in which the displacements are zero. So we saw the nodal points in the video that you saw earlier, right? That actually that is going to be one of the goals as well in the experiment. So yeah. But for a free node, the nodal points are uh, uh, are going to be essentially for each mode we have n plus 1 nodal points or nodes. So for n1, which is mode 1 of the vibration, we have 2 nodal points, right? For n2, we have 3 nodal points. I'm sorry. So for n1, we have 1 nodal points. And for n2, we have 3 nodal points. 1 nodal point, 1 nodal point. For n2, we have 2 nodal points, and n3, I think we are making a very small mistake here. So this is n0, we have 1 nodal point, n1, 2 nodal points, n2, 3 nodal points, and so on and so forth. Okay. So, but the final part is going to be, so far we have only solved the displacement. We haven't solved the temporal part, right? The displacement as a function of time. This was the main equation we were looking at. We can rewrite the equation to look like this, and then we are going to ignore the damping effect for the time being. We will go back to later on. So a general solution for this type of problems is going to look like this, in which you have the general phase shift and everything that you want to find. An and phi n are the unknown constants that are going to be determined with the initial displacement and the velocity of the beam, right? So this is going to be your part T, and we also have the solution for the displacement here. The final solution is essentially a multiplication of the two. Okay. And for this final solution, we can find the nth natural frequency using this equation that which we have seen before. But the next part that we want to talk about, we're actually going out of time, but this is going to be very short, right? We are not going to go into that much detail about this, but we are going to see a video. All right. So this is a cantilever beam. You are pretty familiar with the cantilever beam at this point. It has fixed ends and a free end. The cantilever beam vibration can be modeled by the main vibration equation that we have. The boundary conditions are the things that are going to be different for the cantilever beam. As you can see, the boundary conditions are a little different here. Essentially, at x equals to 0, which is your fixed end, all of the displacement, all of the derivatives of displacements are going to be equals to and the first derivative of displacement is going to be equal to 0, but the second and third derivative of displacement is going to be 0 for the free end. Okay, and this is what the displacement would look like if you were to try. So the general solution for the cantilever beam will look something like this. We can find the beta n multiplied by L by using the n minus 1, the mode minus 1/2 multiplied by pi. So beta 1L, beta 2L, beta 3L, beta 4L, beta 5L, all of them are going to be equals to these, as you can see. And the natural frequency can be calculated using this equation, beta nL squared over 2 pi L squared, square root of EI over rho A, in which n is the mode, L is the length of the beam, E is Young's modulus, and I is the moment of inertia, rho is density, and A is the cross section. So the nodal positions for the cantilever beam can be calculated using by finding the solution to this equation, and we essentially have to put the displacement equals to 0, and the mode shape and the nodal positions are gonna look like this. So in cantilever beam, each mode has n minus 1 nodes. Well, what is damping? Damping is an influence within or upon an oscillatory system that has the effect of reducing, restricting, or preventing its oscillations. In physical systems, damping is produced by the processes that dissipate energy stored in the oscillation. So this is a visualization of damping, as you can see here. This is another visualization of damping, and this is essentially the frequencies, the dying frequencies that you can see are going to die. Okay. So for damping, we actually have a critical coefficient for damping. We had the general solution, if you recall, and for that general solution, just take this out of this analysis for the time being. For that general solution, we can find the roots to be like this, because we know that this is the type of, let's call them quasi-polynomial, but it is not a real polynomial. We can find the roots using this equation, and then your final solution looks like this. So if your C is smaller than C critical, it can be calculated using this. If your C is smaller than that, then you will have a dying vibration, damped vibration. Okay, but why is that? What will happen when your C is smaller than the C critical? So if you look at the main equations we have here, let's say your C is smaller. Let's look at the roots. Let's say your C is smaller than the C critical. It means that your C is smaller than 4mk C squared. Sorry. Okay. So we are going to have an imaginary root to this case, right? to this problem. And imaginary roots are essentially not accepted. So the frequency are not gonna be, which is these roots are referring to the frequency of your system, right? The displacement. So the displacement cannot be sustained because it is giving you an unreasonable root to the problem. But when your C is larger than C critical, the displacement with respect to time is gonna look like this. And for C equal to C critical, your root, you are gonna have the most simple root for the system and the most simple damping mechanism. The damping mechanism can be a course by itself, so I don't know if you have gone over this in your vibration course, but we are not going to go into this that much. We are going to give you the equations you need to solve the problems, and you will learn how to do it with the cantilever beam, essentially, when we are talking more about how to do the calculations for the problem. But eventually what you need to know is the damping ratio, which is a dimensionless term describing how the oscillations of a system decay after a disturbance. And that damping ratio, let's call it epsilon. Epsilon can be calculated by dividing delta by 2 pi. You may want to ask, what is delta? Yeah. Delta is essentially the natural log of your initial displacement versus divided by the displacement at the end cycle, the amplitude, actually, the maximum displacement at the end cycle, multiplied by 1 over that cycle. So that's the delta, and it is called the logarithmic decrement, right? And you can find the damping ratio based on that. But let's watch this video. This is a very long video, so I don't know if you want to go over all of it. Let's go a little ahead. But I want to see you, I want to show you the use. Yes. Yes, cantilever beam here. Yeah, vibration of the wings. So this is what I wanted to show you. What is going on here?
Should power on all of the equipment for you, so you do not need to.
Okay, I just want to show you that vibration is a very important phenomenon, as you are already aware,
worry about that.
In aerospace industry as well.
First, you need to take the measurements as well as angles of this wing, because you will later model it in Pro-E for a modal analysis. Next, you need to pour sand over the entire top surface of the wing. Be sure not to bunch the sand up in any one location. The sand will be used to visualize the nodal patterns that will develop for the different modes of vibration we'll be testing. For the purpose of this demonstration, I'm going to choose the second mode to model. We will tune in the frequency of 34 Hz into the function generator, much like we did.
So keep in mind, in this experiment, the guy here already knows what is the natural frequency for the second mode, right? But we don't necessarily know this. We need to do the calculations to find this.
On the cantilever beam. Using the coarse adjustment knob, we'll reach 34 Hz, and then use the fine-tune adjustment knob to reach the resonant frequency. Telltale signs that we've reached the resonant frequency include maximum deflection of the wing tip, as well as the formation of the nodal point, much like the cantilever beam experiment. When the sand begins to move, you know you're in the right path. As you can see, a nodal point has formed along this line. I'm satisfied that the tip of the wing has reached a maximum deflection, as well as the proper nodal point has formed, and I can now move on to modeling the other modes of vibration that we will be testing. A stroboscope can also be used to get a more exact measurement of the resonant frequency.
Okay, so I guess, yeah, this is going to be it for today. I think we went over time a little bit, but that's all right. It is a recorded lecture, so you can always pause and come back to this. What we are going to do, as I said, we are going to spend 2 labs on this, and then we will move on to the control theory. If we had the time, the control theory lab at this point is just a visualization of a control system and just playing with the setup. So at this point, I'm not thinking of any lab report for that lab. We will talk about it later as we get there. But eventually, afterwards, we'll get to the numerical part of the mechanical testing. And on that numerical part, we probably are going to give you a modal analysis, as the video mentioned, as well as a buckling analysis using ANSYS software. So keep that in mind. Make sure that you understand these basics, like the equations and everything. Then we will get to the modeling later in the semester. Okay, so have a good day and stay safe. Hopefully, I will see you guys pretty soon.